Hello, welcome to week 2 of social network analysis. This week we'll be focusing on modeling social networks. Now, why would you want to model social networks? Just last week we showed how you can learn many interesting things just by analyzing the network structure of real-world networks. What good is a model? Well, a model is going to be a simple representation of that real-world complex network, and it's going to allow you to test certain assumptions, because in order to formulate your model, you have to implement those assumptions and see whether the network that is generated from your model in any way resembles the real-world network that you're seeing. So for example, if you were looking at a social network and you discovered that some people had many more friends than others, well, you could say, oh, well, I think that what's leading to this is just a random fluctuation. So people meet and form edges at random, and some people are going to have more edges and some people are going to have fewer edges. And that's my model. It's going to be a completely random graph model. Well, what happens next is that you can test this. You can generate networks according to your model and see if indeed you get some individuals who have many more friends than others. If this doesn't happen, if your model can't reproduce the distribution of degrees that you see in the real network, well, that means that your model needs to be adjusted, that the way you're thinking about the world and the way that friendship formation functions is actually not what you thought. Your model needs to be extended. These kinds of models also often just serve as a straw man, right? So you know that the model, it's not realistic, right? People don't just meet at random, but you'd like to know exactly how your network is different from such a random network, and that gives you further insight about the measurements that you're taking on your real-world network. Because if your real-world network is looking very similar to say a random graph model, then you can say there's not much interesting going on here. But if it looks very different, if the numbers you get from the model versus the numbers you get in your real network are very divergent, then you can say, aha, this is an interesting feature of my real-world network, and that is what I will pursue further. This very basic network model was first formulated by Erdős and Renyi. They're two Hungarian mathematicians. Erdős was an eccentric. He was very, very productive. He traveled from conference to conference, from one collaborator's door to the next, saying, my mind is open, let's write some papers. And after he would finish the papers, he would move on to the next place. There's actually a network of co-authors that it's prestigious to be close to Erdős in. So if you have an Erdős number of 1, it means you're one of his many, many direct collaborators. If you have an Erdős number of 2, it means you're a collaborator of a collaborator. And so people like to calculate their Erdős number. Mine is 4, by the way, which isn't impressive at all. He collaborated a lot with Renyi, who is actually credited with the quote, mathematicians are just machines who turn coffee into theorems. He and Erdős were very productive, and among their 32 publications are several well-known ones on the Erdős and Renyi random graph model, where they could exactly derive a lot of results about precisely this model of a network where you connect nodes at random. There are basically very few assumptions here. Besides the size of the network, the number of nodes, you just have the probability that any two nodes are connected. This is the probability P. An alternative formulation is that you determine the total number of edges M. And the mathematical treatment is a little bit more difficult in the second case, and in any case the two formulations become very similar once the network is large. So we'll focus on the first one, where you're just fixing the probability that any two nodes are connected. What do these networks look like? Here I've laid out the nodes on a circle, I think it's 20 nodes, and I've added some edges at random. As we learned last week, sometimes the layout is more effective if nodes that are directly connected are close to each other in the layout. So I applied a Spring layout algorithm and got this very typical shape of an Erdős-Rényi random graph. The first thing that we can derive for the Erdős-Rényi random graph is its degree distribution. This tells us how many nodes in the network have no neighbors, how many of them have one neighbor, how many of them have two neighbors, etc. It's going to get a little bit mathematical, but if you've ever had basic probability and statistics, you recognize the binomial distribution. This is all it is. And if you've never had this level of math, don't worry. It's not what I'm going to say. You can also build just through intuition and through playing with the demos. So it's not that you have to derive the binomial distribution from scratch or anything like that. I'm bringing it in more just to show, hey, if you're a mathematician, there's a whole lot of interesting things and properties you can derive about networks. And actually, I'm just going to be scratching the surface of that. So that is the goal, to illustrate how you can intuit some properties when you have a nice model of the network. So again, our model is we have n nodes, and with probability p, we add an edge between every pair of nodes. So we're kind of flipping a coin, right? So one node out of the n is going to look at the n minus 1 other nodes, and for each one it's going to flip a coin to see whether they're going to share an edge or not. Now, to test your understanding, I'd like you to imagine a network, and you're keeping the probability that any two nodes are connected, the value p, you're holding constant, and you're increasing the size of the network, the number of nodes. I want you to think about what happens to the average degree. How many other nodes on average is a node connected to? To help you with this, I have created a NetLogo model. So let me just try and get into that model. And what you're going to do is you're going to make sure that this probability or num is set to probability. You're going to have, you're not going to use this number of neighbors. You're going to fix the probability of linking. Here I've just made it 2%, and we're going to start with 100 nodes. So I'm just going to click this Erdős-Rényi button, and maybe I'll let it lay out just to see what it looks like. So let me try that a few more times. And here I see the average degree. Now I'll increase this to maybe 300 and generate another Erdős-Rényi random graph. I'm also going to look at the average degree. I might do that a few more times, and I might increase to almost 1,000 nodes. Again, generating an Erdős-Rényi random graph. Has to work a little bit harder for a larger graph. And then I'm going to, again, look at the average degree. So see if you can understand what's going on in this case. Now that we've seen what these random networks characteristically look like, we can return to the problem of deriving the degree distribution. The degree distribution is just a probability distribution that's going to say the probability that a node has degree 0, meaning no neighbors, is a certain quantity. The probability that it has 1 is this. The probability that it has 2 neighbors, it's something else, etc. So this is our probability distribution, and the probabilities, of course, have to sum to 1. Back to how this might happen if we're doing a little thought experiment, is that each node is looking at the n minus 1 other nodes, and it's flipping a biased coin, which with probability p is going to say link to that particular node, and with probability 1 minus p is going to say not that one. And the distribution that describes this process exactly, the coin flipping, is the binomial distribution. So what we're interested in is, out of n minus 1 tries, what is the probability that k of them are successful? That is, what is the probability that the node will have degree k? And first we need to know the number of different ways that we can choose k nodes out of n minus 1. This is the binomial coefficient times the probability that you succeeded k times, which is p to the k, times the probability that you failed, n minus 1 minus k times, which is 1 minus p to the n minus 1 minus k. So let's do a little bit of comprehension here. So what is the maximum degree that a node can have in a graph that has n nodes? And here we're assuming that the graph is simple, meaning that you can't have multiple edges between two nodes. It's like two people can only have one friendship. They can't have two or three or four friendships between them. So, and this is the kind of graph that Erdős and Renyi modeled, the simple graph. So what is the maximum degree in this case? Let's delve a little bit more into the binomial distribution. For a lot of you, this will be a review of basic probability, but let's do it nonetheless. So imagine that you have an 8-node graph with a probability p of any two nodes being connected. What we'd like to know is what is the probability that any given node is connected to 4 others. And we're going to color those blue, and the 3 nodes that it's not connected to, we're going to color white. First, we need the binomial coefficient, which is going to say what is the number of ways that you can choose 4 out of 7. Well, you can imagine first that you can uniquely identify all the nodes so that it matters whether, A goes first, B goes second, or B goes first, A goes second, right? And there are 7 factorial different ways of making such an ordering, because for the first spot you have 7 choices, for the second spot you have the remaining 6, the third spot you have remaining 5, etc. So this is 7 factorial if you could distinguish all of the nodes separately. But what we're saying is that we're only distinguishing at the level of whether a trial was successful or not. So whether a node is white or blue, which means that the 3 white nodes are just completely swappable. So our 7 factorial is now divided by a 3 factorial in the denominator, which is the number of different arrangements that we now don't distinguish between. Similarly, for the nodes that we did connect to, there are 4 factorial different ways of ordering them, and now we don't care about their particular ordering, so we have another factor of 4 factorial in the denominator. So in general, this binomial coefficient of choosing, for example here, k items out of n minus 1 is going to be n minus 1 factorial in the numerator, k factorial in the denominator, n minus 1 minus k factorial in the denominator as well. And there should be a parentheses around the n minus 1. Sorry about that. So let's test our understanding. What is the number of ways of choosing 2 items out of 5? Now let's get back to the distribution. Imagine that we have a certain way of choosing the k out of n minus 1. So here it's 4 out of 7. For example, if it was white, white, blue, 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 white, blue, what we would have for the probability of that particular event is 1 minus p times 1 minus p times p times p times p times 1 minus p times p, right? So p to the 4th times 1 minus p to the 3rd. And once we don't care about the particular order of white and blue, we add the binomial coefficient back in. So in the end, the binomial distribution tells us that the probability of a particular node having degree 4 in our 8-node probability p graph is 7 choose 4 times p to the 4th times 1 minus p to the 3rd. And that's it. That's how it works. If p is equal to 0.5, you get this very symmetric looking distribution where it's most likely that the node will have degree 3 or 4, but also it could end up with low probability with no neighbors at all or connected to all 7 of the other nodes. If, however, the probability is only 1/10, then you have a distribution that's much more skewed. It's much more likely that a node will be connected to no others, and very unlikely that it would have anything past degree 4. Once you have this distribution, there are well-known properties such as the mean. The mean is going to give us the average degree. From the binomial distribution, we can tell that this average degree z is going to be equal to n minus 1 times p. And in general, if you had an arbitrary degree distribution, the way that you could calculate the mean is you just take the expected value, which is the sum over all the possible outcomes. Here we're interested in the degree x times the probability of x occurring. To test our understanding, let's see what the average degree would be of a graph with 10 nodes where the probability of any two nodes linking is a third. You can similarly compute the variance. For the binomial distribution, the variance, which is just the standard deviation squared, would be n minus 1 times p times 1 minus p. And it's computed in a very similar fashion, so we won't have to do this in any assignments or anything like that. But in general, you have the expected value of x minus the mean squared, which is the definition of variance, is just this quantity summed over all possible values of x times the probability of each particular value that x can take. The binomial distribution gets quite impractical to compute because the binomial coefficient having those factorials in there just can't be computed for very large numbers. So you typically use approximations. So in the limit of p being small, you can use the Poisson distribution. And in the limit of the graph being large, so n is large, you can use the normal distribution. And the way that both the Poisson and normal are going to look for large graphs is that it's going to be a nicely symmetric distribution around the mean value k. Of course, if the probability is very, very low, then the Poisson distribution actually is not symmetric, right? It might be very much hitting up against degree 0 and then going from there. But the main point to take away is that we're not going to be seeing many nodes that have, say, a degree that's many times higher than the average degree. That's something you simply don't see, and this is because this probability drops off exponentially here as you get higher and higher in degree. So the basic insight that we get out of this is that there are no hubs. Hubs in the sense of some nodes that have extremely high connectivity, extremely high degree. You just don't see this.